We're going to continue our work on factoring polynomials, and we're looking at some special polynomials or some special products. And today we're talking about some binomials. So that means that our polynomials are going to have two terms, and we're going to be looking at these two terms being perfect squares. So we have two special products, and let's look at the first one. This one's called the difference of two squares. So look at number one here, x squared minus 121. You can see that we have a binomial, so we have two terms. And you can see that it's a difference because there's a subtraction sign between the two terms. And the first term is a perfect square, x squared. And then the second term is 121, which is 11 squared. This first example would be a very good example of a difference of two squares. And we squared the x, right? I'm putting parentheses just to make a point. We squared the x for the first term, and then there's a difference, and we squared an 11 for the second term. Get the 121. So when we have a product that looks like that, you may recall from our earlier work in polynomials and multiplications that this will then be factored as conjugates. We're going to be using conjugates here. So that means that one binomial will have a plus and the other one will have a minus. And we take the square roots of those numbers that are out there. So x plus 11 times x minus 11. So let's just remind you with a check that this really does work. If we FOIL this, we get x squared. So here's our check. And then with our outers, we get a negative 11x. And with our inners, we get a positive 11x. So see how having that positive and negative opposing signs there makes those middle terms equal to 0. And then when we multiply our two last terms, there's our negative 121. This one's called, again, let's go up here and look at the box. It's called the difference of two squares. You will have a subtraction sign and you will have two squares as your terms. And how we factor that is by using the conjugates. These are called conjugates. One plus and one minus. Okay, so in number 2, 81 minus y squared, we still have a binomial with two terms and it's a difference. And we do have a perfect square, 81, because that's 9 squared, isn't it? So we have 9 squared. And then, of course, we have the y that's being squared. So we definitely have a difference of two squares. Binomial, and so we know we're going to have to use some conjugates, so go ahead and put the parentheses down, and then we know we're going to have a plus and a minus. And now don't be disturbed by the fact that that 81 is in front rather than the variable. We get used to putting the y squared or x squared in the first position, but that's okay. Because the 81 is in front of the binomial, it's the first term, then we're going to put the 9s first when we go to factor, okay? And then here we just put the y's. And it's very important that you do put the 9s first, because if you put the y's first, then when you multiply the check, you'll notice that that binomial is y squared minus 81. But the original binomial was 81 minus y squared, so it's important to leave these in that order. Okay, hope that makes sense. Let's take a look at number 3. Okay, with number 3, these don't look like squares. It is a binomial, but maybe you notice that number 3 has a GCF. So our first step will always be to look for that GCF. Remember, we've been training for that. And so in this case, the GCF is 5x. So we're going to go ahead and factor that out first. So 5x is our GCF, which leaves behind x squared minus 100. And now that binomial is the difference of squares. So that binomial then we are going to factor using conjugates, and it's going to be an x plus 10 and an x minus 10. Good work. 72x squared minus 98, that's number 4. I'm going to ask you to pause the video and give this one a shot. Okay, and when you unpause the video, I'm going to have my answer. So pause your video now. Okay, how did you do? Did you notice that there was a GCF of 2, so that needed to be factored first, which left us with 36x squared minus 49. And both of those are perfect squares. The 36x squared is 6x being squared, and the 49, of course, is 7 squared. So I used the conjugates there, and our final answer is 2 times 6x plus 7, 6x minus 7. By the way, those binomials, those can be in any order. If you put the 6x minus 7 first before the 6x plus 7, that's okay. That's still the same answer. Now, with this next one, we do have a binomial. That 625 is a perfect square for sure, because this is 25 being squared here. Okay, we have a difference. What about x to the fourth? Is that a perfect square? Yes. Yes, it is, because it's x squared squared. Matter of fact, I want you to see what the perfect square powers of x are. I'll just see if you can see a pattern. So on the first column, I put the first 6 powers of x, and I'm going to square each of these. So when I square x, of course I get x squared. And when we square x squared, we get x to the fourth. And when we square x cubed, we get x to the sixth. Now remember, we're using our power rule, which means that we're going to multiply those exponents. So x to the eighth. So are you noticing on the right-hand side what kind of powers we're getting for the squares? Yes, do you see the pattern? So even powers of x are perfect squares. Even powers of your variable are going to be perfect squares. So x to the fourth is definitely a perfect square, and it's x squared squared. So I hope that makes some sense. Some little tip to help you as you do these problems. So how do we then factor that? Well, conjugates, right? So we're going to have x squared plus 25 times x squared minus 25. Okay, well that's cool. Now here's the kind of neat part. I see another difference of squares. Do you? Look at this. This binomial here, x squared minus 25, that is a difference of squares. So we can keep factoring. That's what that says. So I'm going to go ahead and keep factoring that. So we can definitely use our conjugates here, and that will be an x plus 5, x minus 5. So notice it's always a good idea to look at your final answer before you're done and see if you can possibly factor further. And in this case, we can. But then let's look at that x squared plus 25. That's called the sum of squares. And the sum of squares is prime. That means it does not factor further. So we bring down the x squared plus 25. Now I have to tell you that sometimes my students want to put this answer for x squared plus 25. They want to tell me that it's x plus 5 squared. Okay, but let me just remind you that if you square x plus 5, that we get a middle term. Okay, so here I am doing my foiling, and notice that we get a middle term of 10x. So x squared plus 25 cannot be factored as x plus 5 squared. As a matter of fact, something that you want to know, and let me show you with the table. Look at this. The sum of two squares is prime. That means it does not factor. Put that in your table in your notebook, that the sum of two squares does not factor. Okay, other than if there's a GCF. Okay, so you always will look for that.